Among the deepest questions in physics lies the black hole information paradox, a conflict that challenges the foundations of both quantum mechanics and general relativity. At its core, this paradox asks, what happens to information that falls into a black hole? Does it vanish forever, or is it somehow preserved? The resolution to this mystery could fundamentally change our understanding of the universe. To unravel this enigma, let's dive into the fascinating worlds of black holes, quantum physics, and the very nature of reality. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity, creating a singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, a boundary beyond which nothing can return. Once something crosses the event horizon, it's thought to be lost forever, or is it? This question lies at the heart of the information paradox. To understand the paradox, we first need to grasp what physicists mean by information. In quantum mechanics, information refers to the specific state of a system, everything about the particles, their positions, velocities, and quantum properties. A fundamental principle of quantum mechanics is that information cannot be destroyed. This idea is tied to the concept of unitarity, which ensures that if you know the state of a system at one point in time, you can, in theory, trace its past or predict its future with perfect accuracy. However, black holes seem to defy this principle, creating a glaring contradiction between quantum mechanics and general relativity. The black hole information paradox emerged in 1974 when physicist Stephen Hawking made a groundbreaking discovery. Using quantum field theory in the curved spacetime near a black hole, Hawking showed that black holes are not entirely black. They emit a faint glow of radiation, now called Hawking radiation. This radiation arises because of quantum fluctuations near the event horizon, where pairs of virtual particles constantly pop into existence. Normally, these particle pairs annihilate each other almost instantly. But near a black hole, one particle can fall into the black hole while the other escapes, becoming real and forming Hawking radiation. Here's the catch. Hawking radiation is completely thermal. It contains no information about the material that fell into the black hole. As the black hole emits this radiation, it loses energy and gradually shrinks. Eventually, it could evaporate entirely, leaving nothing behind. This creates a serious problem. If the black hole disappears, what happens to the information about everything that fell into it? If the information is truly lost, it violates the principles of quantum mechanics. But if the information is somehow preserved, it contradicts the classical understanding of black holes in general relativity, which states that nothing can escape the event horizon. This paradox forces us to confront a deep conflict between the two pillars of modern physics. General relativity describes the gravitational behavior of large-scale objects like stars and black holes. Quantum mechanics describes the behavior of particles on the smallest scales, where probabilities and uncertainties reign. Resolving the paradox could require a unified theory that combines these two frameworks, often referred to as quantum gravity. Over the decades, physicists have proposed numerous ideas to solve the information paradox. Here are some of the most intriguing theories. 1. Information escapes with Hawking radiation. One possibility is that information is encoded in the Hawking radiation itself. Though initially thought to be purely random, it's possible that subtle quantum correlations in the radiation carry information about the black hole's contents. However, this idea requires a mechanism for encoding and transmitting the information, which remains unclear. 2. The holographic principle. The holographic principle suggests that all the information about a three-dimensional region of space, like the interior of a black hole, can be encoded on a two-dimensional surface, like the event horizon. According to this idea, the event horizon acts like a hologram that stores the information. This theory ties into the concept of ADS, CFT correspondence, a groundbreaking idea in theoretical physics that relates gravity in higher dimensions to quantum field theories in lower dimensions. 3. Firewall hypothesis. The firewall hypothesis posits that the event horizon is not a smooth boundary, as general relativity suggests. Instead, it might be a searing wall of high-energy particles that destroys anything trying to pass through. This would prevent information from being lost inside the black hole, but it clashes with our current understanding of spacetime. 4. Wormholes and quantum entanglement. Some theories propose that black holes might be connected to the rest of the universe through wormholes or quantum entanglement. In this view, the information is not lost but instead remains accessible through these connections. This idea has gained traction in the context of the ER equals EPR conjecture, which links wormholes, Einstein-Rosen bridges, to quantum entanglement. 5. Remnants. Another possibility is that black holes don't completely evaporate. Instead, they leave behind small, stable remnants that retain the information. However, this solution raises new questions about the nature and stability of these remnants. The black hole information paradox is more than a theoretical puzzle. It strikes at the heart of our understanding of reality. Solving it could 1. Unify physics. It might lead to a long-sought theory of quantum gravity, reconciling the inconsistencies between quantum mechanics and general relativity. 2. Reveal the nature of black holes. We could learn more about what happens inside black holes, including whether singularities and event horizons truly exist as we imagine them. 3. Advance quantum computing. Understanding how information behaves in extreme conditions could revolutionize our approach to quantum information science. As of now, the black hole information paradox remains unsolved. Physicists around the world, armed with new tools like the Event Horizon Telescope and quantum simulations, continue to probe the mysteries of black holes. Stephen Hawking himself suggested late in his life that information might be preserved in a chaotic form, encoded in the event horizon structure. The paradox reminds us that the universe still holds profound mysteries, and solving them requires us to rethink our most fundamental assumptions. Black holes, once thought to be simple objects, have become gateways to the unknown, profound reminders of how much we still have to learn about the cosmos. In the words of physicist Leonard Susskind, the information paradox is not just a paradox about black holes. It's a paradox about the laws of physics themselves. Who knows? The answer might just unlock the deepest secrets of the universe.